Welcome to Animal Behavior. Today, we are diving into one of the most fascinating phenomena in the natural world: honeybee foraging and dance communication. Imagine trying to give your friends precise directions to a hidden food stall in a pitch black, crowded room without using your phone or speaking a single word. This is the exact challenge a honeybee faces every single day. To ensure the survival of their colony, these incredible insects have evolved a complex physical language to recruit their sisters to rich flower patches. Let us explore exactly how they do it. Now that we understand the challenge, let us look at why this communication is so vital. A honeybee colony consists of tens of thousands of individuals. They require massive amounts of nectar and pollen to survive the winter. If every bee flew out blindly to search for food, they would waste enormous amounts of energy, and the colony would likely starve. Instead, a few scout bees explore the surroundings. When they find a rich nectar source, they return to the completely dark hive. Since they can't point or use visual cues, they use a physical language based on movement and touch. This turns a random search into a highly coordinated harvesting operation. This brings us to the first of the two main dances, the round dance. Think about telling a friend about a coffee shop just around the corner. You do not need to give them exact GPS coordinates. They will see it when they step outside. Bees use the round dance for food sources located very close to the hive, typically within a radius of 50 to 100 meters. The returning forager runs in a tight circle, reverses, and repeats. She also shares a drop of nectar so her sisters can taste the sugar and memorize the floral scent. However, she provides absolutely no directional or distance information. The recruited bees simply fly out and search nearby until they find that specific smell. But what happens when the food is not just around the corner? For food sources located further away, typically beyond 100 meters, the bees use a much more sophisticated system called the waggle dance. This dance acts as a biological GPS system. The bee performs a figure-8 pattern, but the most critical part is the straight central portion, known as the waggle run. During this run, she vibrates her abdomen rapidly and produces a low-frequency buzz with her wings. The genius of this behavior is that it encodes two distinct pieces of mathematical information simultaneously. It tells the receiving bees exactly how far to fly and exactly what angle to take relative to the sun. Let us break down exactly how this biological GPS works, starting with distance. As a scout bee flies to a flower patch, she measures the distance by tracking how much the visual landscape moves past her eyes. This visual tracking is a concept known as optic flow. When she returns to the hive, she must translate this experienced flight distance into a physical movement. She does this by adjusting the length of time she spends performing the straight waggle run. It is a beautiful biological rate equation. The longer the bee waggles her abdomen, the further away the food source is located. This relationship between time and distance can be expressed with a simple and elegant formula. The formula is D equals K times TW. Let us define what each of these symbols means. The variable D represents the total distance from the hive to the food source, measured in meters. The variable TW is the duration of the straight waggle run, measured in seconds. Finally, K is a proportionality constant. This constant varies slightly depending on the bee species and environmental conditions, but it generally equates to about 750 to 1,000 meters per second of waggle. Physically, if the bee increases her waggle time, the calculated distance increases proportionally. Before we move on, let us see this formula in action with a concrete example. Suppose a researcher observes a returning forager bee inside the hive. Using a stopwatch, they measure the straight waggle run and find that it lasts for exactly 2.5 seconds. We are given a known proportionality constant for this species of 800 meters per second. We want to find the total distance to the food. We start with our formula and substitute the known values, multiplying 800 by 2.5. This gives us a final answer of 2,000 meters, or 2 kilometers. Physically, this means the recruited bees must fly exactly 2 kilometers away to find the specific flower patch. Now that we have calculated the distance, we must address the second half of the puzzle, direction. Inside the completely dark hive, bees cannot see the sun. Furthermore, they build their honeycombs vertically, hanging straight down. The absolute genius of the honeybee is that they use the vertical pull of gravity inside the hive to represent the direction of the sun outside the hive. If a bee dances pointing straight up the honeycomb, she is telling the others to fly directly toward the sun. If she dances pointing straight down, she means fly directly away from the sun. Any angle she makes relative to straight up corresponds exactly to the angle the bees must fly relative to the sun. This directional mapping gives us our second mathematical relationship. The formula is theta d equals theta f. Let us look at what these symbols represent. The symbol theta d is the angle of the straight waggle run relative to straight up, which is vertical gravity on the honeycomb. This is measured in degrees. The symbol theta f represents the angle the recruited bees must fly relative to the current position of the sun in the sky, also measured in degrees. In plain English, the angle of the dance on the vertical comb is exactly equal to the angle of flight relative to the sun. If the bee alters her dance angle, the required flight angle changes by the exact same amount. Let us apply this directional concept to a real-world scenario. Imagine a scout bee finds a patch of blooming apple trees. As she flies to the trees, she notes that the sun is exactly 60 degrees to her right. We need to determine what angle she will use for her waggle run inside the dark hive. First, we define the flight angle. Since the food is 60 degrees to the right, our theta f is positive 60 degrees. Because our formula states that the dance angle must equal the flight angle, we conclude that theta d is also 60 degrees. Physically, the scout bee will perform her waggle run pointing 60 degrees to the right of straight up on the honeycomb. To truly solidify this concept, let us look at a visual representation of the waggle dance mapping. On the left side of the diagram, you see the inside of the hive. The honeycomb is oriented vertically, with an arrow pointing down to represent gravity and a dashed line pointing straight up. The bee is performing her waggle run at a 60-degree angle to the right of that vertical line. Now, look at the right side of the diagram, representing the outside world. The hive is at the center, and a dashed line points directly toward the sun. The flight path to the flower patch is exactly 60 degrees to the right of the sun line. This perfectly illustrates how an angle relative to gravity translates to an angle relative to the sun. So we have seen the formulas and how they work, but how do we know this is actually true? This brings us to the brilliant experimental proofs by Carl von Frisch, which won him a Nobel Prize. He did not just guess, he proved these mathematical models step by step. To prove the distance component, he set up a feeding station with sugar water at a specific distance, say 200 meters, and marked the visiting bees with paint. When they returned, he measured their waggle runs. He then moved the feeder to 500 meters and then 1000 meters, recording the times again. He found a perfect mathematical correlation. As the physical distance increased, the waggle duration increased proportionally, proving our distance formula. Now that the distance model was proven, von Frisch needed to prove the direction component. He placed a feeding station at a specific angle relative to the sun. To test if the recruited bees were actually following the angle communicated in the dance, he set up several identical, empty feeding stations at different angles in a circle around the hive. He observed that the recruited bees overwhelmingly flew to the station at the correct angle, completely ignoring the others. To be absolutely certain, he even used mirrors to change the bees' view of the sky, tricking them into dancing at the wrong angle. This definitively proved that they were using the sun as their compass and gravity as their map. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that the round dance allows bees to efficiently exploit nearby resources by sharing scent and quality information without needing complex directions. Second, for food further away, the waggle dance transmits precise mathematical coordinates. We saw how time is used to represent distance and how the vertical pull of gravity is used to represent the sun's angle. Finally, we saw how Carl von Frisch proved these concepts experimentally. Ultimately, this incredible communication system transforms a collection of individual insects into a highly coordinated superorganism, capable of thriving in complex environments. You now understand the language of the honeybee.